This is the final lecture before your test. So your test is on Monday, May 30th, and it will be on all of the lectures that we've covered so far. And there will not be a lecture posted that day. Your only responsibility is to take the test. It will be an hour and 20 minutes long. And again, it is 30% multiple choice, 60% short answer, and 10% quiz or essay. So today we're talking about economy and lactate threshold. For the outline, you guys will be calculating energy expenditure, so kcals and METs, which are metabolic equivalents. We will talk about exercise economy, so you should be able to determine who's a more economic exerciser at the end of this, and then we will be discussing lactate threshold. Just a little bit of extra info on VO2 max. I forgot to put it at the end of last lecture. So if you are calculating VO2 max, just so you guys have some reference numbers to know what is a normal VO2 max value, the highest ever recorded VO2 max is 98 milliliters per kg per minute, and that was done by a cross-country skier. The average VO2 for cross-country men is between 60 and 70 milliliters per kg per minute, so these are obviously very fit people. So this is on the higher range of VO2 max values. Whereas cross-country women, who again are very fit, their VO2 max is usually between 50 and 60 milliliters per kg per minute. So here you can see that women, even though they're very fit, if they're running cross-country regularly, they have high VO2s, but it is lower than men. And then you are not doing so hot, not super fit values if your VO2 max is 30 milliliters per kg per minute or less. Average VO2 values are generally between 40 and 45 milliliters per kg per minute. So just in case you are calculating VO2 and you get a number that's 1,000 milliliters per kg per minute, you should just have a little flag going off in your head that that's probably incorrect and you need to check your math. And now just a review of how to calculate VO2, going back and forth between absolute and relative VO2, because we're going to need to be able to do that for the rest of these calculations. So if we take Liam Hemsworth and we're going to assume that he's 70 kilograms and his VO2 is 1.32 liters per minute. So this is not his max. This is just him exercising at a normal and moderate intensity. And so then you guys should be able to answer if this is absolute or relative units. And it is absolute units because we are not accounting for body weight. There are no kgs in these units, so it is absolute. And if we compare Liam to Chris, his brother, who's 90 kilograms, and his VO2 is going to be 1.84 liters per minute. So this is absolute terms, and if we want to convert that to relative terms, all we have to do is divide the absolute VO2 by their body weight. So for Liam, we take 1.32 liters per minute. We're going to multiply it by 1,000 milliliters to convert it to milliliters rather than liters. You can leave it in liters, but it's just an easier number to deal with if you convert it to milliliters. So you multiply by 1,000, and then you divide by body weight, which was 70 kilograms. So Liam's relative VO2 at this intensity is 18.8 milliliters of oxygen per kg of body weight per minute of activity. And for Chris, do the same thing. Take 1.84 liters per minute, multiply it by 1,000, and divide by body weight, 90 kilograms, to get 20.4 milliliters per kg per minute. So you guys should be able to go back and forth. If I give you relative VO2, you should be able to convert that to absolute and vice versa. Now if we want to calculate energy expenditure in kcals, which is how we measure human energy expenditure, is through kcals. The basis of what you need to know to be able to calculate kcals is when you consume 1 liter of oxygen, this produces 5 kcals of heat. Remember, heat is how we can estimate someone's metabolic rate and energy expenditure. So when I breathe in 1 liter of oxygen, this is going to be equivalent to producing 5 kcals of heat. So 1 liter of oxygen equals 5 kcals. If we want to determine how many kcals per minute a person used during an activity, if we use Liam again, so he's 70 kilograms and his VO2 at this intensity in absolute terms was 1.32 liters per minute. And Chris was 90 kilograms, his VO2 was 1.84 liters per minute. To determine how many kcals per minute used, you take their absolute VO2, 1.32 liters per minute, and multiply it by 5 kcals, and you end up with 6.6 kcals per minute. So Liam is using 6.6 kcals per minute of activity, and that 5 kcals came from up above where it says 1 liter of oxygen is equal to 5 kcals. And since 1.32 liters of oxygen are being used per minute, then we just multiply that by 5 kcals in order to determine how many kcals per minute are being used. So with Chris, you do the exact same thing. You take his absolute VO2, 1.84 liters of oxygen per minute of activity, multiply that by 5 kcals, and you get 9.2 kcals per minute. So Liam and Chris's energy expenditure is 6.6 kcals per minute and 9.2 kcals per minute. What if we want to know how many kcals are being used in 30-minute period? Now, you just have to multiply the amount of kcals being used in 1 minute. So for Liam, it was 6.6 kcals per minute, and multiply it by 30 minutes. And then you will get 198 kcals for a 30-minute period. And if the time changes, if I tell you an hour, then you just substitute 30 minutes for 60 minutes. Same thing with Chris, 9.2 kcals per minute, which we calculated from the previous slide. Multiply that by 30 minutes, and you get 276 kcals in a 30-minute period. Another way we can calculate energy expenditure is through METs. And a MET stands for metabolic equivalent. And this tells us how intense an activity is. So 1 MET is equivalent to 3.5 milliliters of oxygen per kilogram of body weight per minute of activity. Resting VO2 is 3.5 milliliters per kg per minute, and this is true of everyone. So if I measured your VO2 right now, if you guys are all at rest, and I hooked you up to indirect calorimetry and calculated your VO2, measured your VO2, everyone's VO2 would be about 3.5 milliliters per kg per minute, because this is in relative terms since we did divide by body weight. So everyone's resting VO2 is about 3.5. That's why we can assume that 1 MET is the same for everybody, because if I measure it on all of you, it is all about 3.5. So to calculate a MET, you just take someone's relative VO2 and divide that by 3.5 milliliters per kg per minute. And that's how you determine how many METs a person is exercising at, or how intense an activity is. If we want to calculate how many METs is a certain exercise, for Liam, if his VO2 for a given activity is 18.8 milliliters per kg per minute, and Chris's is 20.4 milliliters per kg per minute, and we want to calculate how many METs is this exercise so we know what intensity they're exercising at, you would just take their relative VO2, 18.8 milliliters per kg per minute, and divide it by 3.5 milliliters per kg per minute, and you get 5.3 METs for Liam. Same thing with Chris, 20.4 milliliters per kg per minute, divide that by 3.5 milliliters per kg per minute, and you get 5.8 METs. So we have these numbers, 5.3 and 5.8 METs, but what does that mean? So this is the guidelines for determining how many METs is equivalent to what intensity of exercise. So light physical activity is considered 3 METs or less. whereas moderate physical activity is between 3 and 6 METs, and then vigorous physical activity is 6 METs or higher. So how many METs is this exercise again from Chris and Liam? Liam was exercising at 5.3 METs, whereas Chris was exercising at 5.8 METs. So based on these criteria, were they exercising at light, moderate, or vigorous physical activity? They were exercising at moderate exercise activity because they are between the 3 and 6 MET range. So when you guys are calculating energy expenditure, remember that kcals, you have to use absolute VO2. It doesn't work if you use relative VO2. And METs, you have to use relative VO2. And then just for later on, we learned about RER in the previous lecture. And just remember, to calculate someone's RER, you also have to use absolute VO2. You can't use relative. All right, now let's move on to exercise economy. So I think it's easiest to understand economy if we think about cars. So we say a car is more economic if that car can travel a further distance on a given amount of gas. So you see how many miles can that car travel in 1 gallon of gas. Or how economic is a car if it uses less gas for a given distance. So the car has to drive 50 miles, and which car uses less gas? That is going to be the more economic car, the one who uses the least amount of gas. So cars, we can use distance and gas, and we can compare that to humans using intensity and oxygen. So humans are more economic if they can exercise at a higher intensity for a given oxygen consumption. So if we know that someone is exercising at 10 milliliters per kg per minute, whoever is exercising at a higher intensity, if we're comparing two people whose oxygen consumption are the same at 10 milliliters per kg per minute, the person exercising at a higher intensity is more economic. Or if we're comparing people exercising at the same intensity, whoever has the lower oxygen consumption is the more economic person. So distance is equivalent to intensity between cars and humans, and gas is equivalent to oxygen between cars and humans. So if we want to determine who's the more economic runner between LeBron and Stephen Curry, we can look at VO2 on the y-axis in milliliters per kg per minute. We have to use relative terms because we're comparing two different people. And then we have intensity on the x-axis, and we're increasing from 1 mile per hour up to 11 miles per hour. So at a given intensity, if we look at a set intensity, who's more economic, LeBron or Curry? It's going to be the person with the lower VO2. So at a given exercise intensity, whoever is using the least amount of oxygen, so whichever car is using the least amount of gas, is the more economic one. If we look at 8 miles per hour and we want to determine at this given intensity of 8 miles per hour, who's more economic, LeBron or Curry? So LeBron is using about 37 milliliters per kg per minute, and Curry is using about 35 milliliters per kg per minute. So who's more economic, LeBron or Curry? Curry, because he has a lower VO2 at a given intensity of 8 miles per hour. He is using less oxygen at a set intensity. And you can look at this the other way. So if we want to look at who's more economic based on their VO2 data, so if two people have the exact same VO2, who is more economic? A person exercising at the higher intensity. So here, if we're looking at a VO2 of 25 milliliters per kg per minute, LeBron is exercising at about 5.5 miles per hour, and Curry is exercising at 6 miles per hour. So again, Curry is the more economic person because he's exercising at the higher intensity, 6 miles per hour, at a given VO2. So the car is going a further distance for a given amount of gas. There are a few determinants of economy. One is mechanics. So if you think about people running, if you just are walking around and you see different people running, some people have very big movements when they are running. They bounce up and down a lot, and they seem to be putting more effort into moving up and down rather than propelling themselves forward. Whereas if you look at cross-country runners, they are very efficient and they have very small movements in general in like their upper body, and they are very good at propelling themselves forward. So if you have big movements, you're wasting a lot of energy, and so you are less economic. And I think the easiest way to show this is if you click this YouTube link and watch this scene from Friends. Rachel is the more economic person, whereas Phoebe is much less economic because she has very large movements. So funny moment for you guys to interrupt your exercise physiology. Bigger movements means you're less economic. Another determinant of economy is muscle fiber distribution. We're going to get into this muscle fiber distribution much more in the next section of material. But in general, type 1 fibers are known as the slow twitch aerobic fibers. So they participate in oxidative phosphorylation much more compared to type 2 fibers, which are the fast twitch fibers, anaerobic. So they do not participate in oxidative phosphorylation as much. And the more economic fiber is type 1. They are better at utilizing oxygen compared to type 2 fibers. So if a person has more type 1 fibers, they're likely to be more economic compared to someone that has more type 2 muscle fibers. And one of the determinants, we talked about how a more fit or unfit person is who has the higher VO2 max. And if you max test the entire cross-country team, they're all going to have pretty similar VO2 maxes, and they're all going to be very high. So that's obviously not the only determinant of exercise performance, because not all of those runners are going to get first in their meet. So one of the factors that also determines exercise performance are mechanics and muscle fiber distribution. So how economic a person is. And generally, if you have two people that have very similar VO2 maxes, whoever is more economic will probably win the race. Now let's talk about lactate threshold. So lactate, we've talked about lactate in the past. When is lactate produced? It's always being produced, even when we're at rest, but we produce more lactate at higher intensities because we have fast glycolysis going more when we're exercising at high intensities, and therefore we're going to be producing more lactate. Okay, so higher intensities, more lactate production. And then how do we clear out this lactate from our blood? So lactate can be converted to glucose via gluconeogenesis. It is also used in the lactate shuttle, and once lactate is used in the lactate shuttle, it's converted back to pyruvate. And also the brain can actually use lactate for fuel. So there's other places that lactate can be used, but these are three main ways that we've talked about a little bit. Is lactate can be converted to glucose and then be used in glycolysis, the lactate shuttle, and the brain can actually use it for fuel. And if we break down one lactate molecule, that actually provides about 15 ATP molecules. So it can be used to produce ATP. So lactate threshold is the point where lactate production exceeds lactate clearance. And that can be shown here. So on the y-axis, we have lactate, which is in millimoles per liter of blood. And on the x-axis, we have running speed. So we're increasing the intensity. You can see that lactate stays pretty steady between 5 and 8 miles per hour. And then it has a big increase all the way up to 13 miles per hour. So the point where lactate threshold occurs is here, the point right before lactate production exceeds lactate clearance. So right here on this flat portion, lactate production is equivalent to lactate clearance. I think of it like a cookie. If you give me one cookie a minute, I can eat that cookie and clear out the cookie. So you are producing 1 molecule of lactate a minute, and I am clearing out 1 molecule of lactate a minute. So we're going to stay steady down here. There is not going to be an accumulation of lactate. Whereas here, now lactate production is greater than lactate clearance. So if you increase you giving me a cookie to once every second, then I cannot clear out a cookie a second. It takes me longer than a second to eat a cookie. So here, the body is producing much more lactate than it can get rid of. And that's when we've reached lactate threshold. So what causes this increase in lactate production? Why do we suddenly have so much more lactate production and our body can't compensate with adequate lactate clearance? When we increase our exercise intensity, we increase our ATP need. Therefore, fast glycolysis is going to be going faster. And if fast glycolysis is going faster, we are producing more lactate. So if you continually increase your intensity, you're going to be producing much more lactate. So how would lactate threshold affect performance? Once you reach lactate threshold, you have a pretty limited time left to exercise if you continue to exercise at that intensity. So you either need to back off and decrease the intensity so you're not producing as much lactate, or you are just going to not be able to exercise as long. You're going to have to stop if you continue at that intensity. So why? Why is it going to decrease the time left to exercise? Because if you have a lot of lactate, this inhibits PFK, phosphofructose kinase. And if you remember that this is the rate-limiting enzyme of glycolysis and glycogenolysis. So if PFK is inhibited, glycolysis is not going to be going as much. If PFK is activated, then glycolysis will be going more. And therefore we will be producing more pyruvate and more ATP. But because lactate is inhibiting PFK, we're going to decrease our glycolysis rates, decrease our pyruvate production, and therefore that pyruvate can't go onto the Krebs cycle, and we're going to decrease our ATP production. So athletes really train to push this out to a higher intensity so that they can continue to exercise at high intensities without having a lactate accumulation. And you can see that here. So this solid line is an untrained person, and their lactate threshold occurs at about 250 watts, whereas the trained person, the dotted line, their lactate threshold doesn't occur till 275 watts. So this trained person can continually exercise at 275 watts without accumulating a lot of lactate. They can exercise at a higher intensity. Whereas this untrained person can only exercise at 250 watts before accumulating lactate. And that's ideal. If you want to win the race, you have to exercise at a higher intensity. So if you're comparing this trained and untrained person, the trained person is probably going to win because they're exercising at a higher work rate. So then they're not going to have lactate threshold until a later intensity. That was a quick lecture. So you guys have plenty to study. If you have any questions, let me know. Again, your test is Monday, May 30th. And have a good time studying.